So let's continue to look at applications of quadratic functions, specifically when are we looking at minimums and maximums. And so the other day we looked at projectile questions, and so that was an example that we did from page 347 in your workbook, class example number 1. Today we'll look at revenue and area problems. So page 348, class example number 2, we have a hockey club that has 7,200 season ticket holders, and the current cost is $1,400. And our owner is looking to generate more revenue, maximizing his revenue, and so a market research company indicates that for every $25 increase in price, we are going to lose 100 season ticket holders. And so obviously there's the debate that can happen as to whether or not that's something you want to lose ticket holders. But if we're strictly looking at numbers and looking at maximizing revenue, then this is a really good look at applications of quadratic functions. So putting this function together then, so we need to consider revenue at its most basic understanding. So revenue meaning the amount of money that we are bringing in. Revenue at its most basic is simply the cost multiplied by the quantity. So how much are we selling something for, and how many are we selling? So if we take a look at this problem, the current revenue is going to be the cost, $1,400, and we're selling 7,200. And so a quick calculation on that tells us that our current revenue is $10,080,000. However, we're going to be changing some things up. So our new cost is going to start at $1,400, but because we are looking at increasing the price by $25 increments, however, we don't know how many increments we're going to do, so that is where it makes sense to set your variable x to be the number of $25 increases. So we know our new cost then is going to be $1,400 plus 25 times the number of increases. So if x is 1, we increase it by 1 increment, so therefore the price would be $1,425. If x is 2, $1,450, and so on and so forth. Then that also affects our quantity, so our new quantity will then be 7,200, our current number, and it's going to decrease by 100 every single time we increase it by 25. So if we increase it by 25 once, x equals 1, then we lose 100. If we increase it by 25 twice, x is 2, then we lose 200. If we increase it by 25 3 times, so $75, then we lose 300. So that would be 7,200 minus 100x. So x is the number of $25 increases. So our new revenue then is going to be new cost times new quantity, or 1,400 plus 25x cost times new quantity, 7,200 minus 100x. So take a moment and expand. You can use FOIL, you can use a box diagram, area diagram, and let's just hit pause and come together in a moment. So you should have then 10,080,000 plus 40,000 x minus 2,500 x squared. So take a moment then and understand what that's going to look like once we graph that in our calculators. So instead of our y-axis, we have an r-axis representing revenue. Our x-axis is representing the number of $25 increases or increments. And it's important to understand what these axes represent, because when we graph it, what does the data mean? We're looking only at quadrant 1 because presumably we're not going into a negative revenue and we're not decreasing our price. Rather, we should be increasing our price. So we know that if there are no increases, our current revenue stands at $10,080,000. So that should be, let's hypothetically say that it's there, and things will go up, and then we increase it enough that people will just leave and not want to pay the money, and we end up with zero revenue. So let's take a look at that on our calculators. So in your calculator, then if you enter that in for y equals, and we hit graph, your calculator isn't seeing it. So a few ways. We need to obviously adjust our Windows setting, and some people just start playing around and put in some random values. Some of you guys might think, well, the y max has to be greater than 10,080,000. Another way to go through this is to use Zoom. And what I would suggest is if we go down to Zoom 0 is Zoom Fit. And what Zoom Fit does is it's not going to give us perfect Windows settings, but it will help us to find our graph. And there we can see it. We can now see our y-intercept. We can kind of make out a maximum. So let's take a look at these window settings, and we'll need to adjust them. So we can see we've got some random numbers here. My y minimum, I'm going to make that something that is negative so that I can actually see the origin and see the x-axis. So maybe I make that negative 20,000. And my y max, maybe we need to go larger than 10,080,000, so maybe we go to 11 million. And perhaps we should be counting up by something more than 1. Perhaps we count up by 100,000. We could do that. So let's take a look at what that looks like. Okay, so I need to count up by something perhaps smaller, so that, or larger, sorry, so that I'm not getting these ticks so close together. Perhaps I should count up by 1 millions. We can also see that we need to increase our X max as well. So let's increase our X max. Perhaps we'll make that 100, and then we'll count up with a scale of 10, and my Y scale, perhaps we'll look at counting up by 1,000,000 and see what happens. There we have it. Great. So we can see the increments. That also helps us to give some estimates as well. So let's go back and take a look at these questions then. So it asks us to determine the price of a package of season tickets that would generate the maximum revenue. So when we look at this, we know that the maximum occurs right about there. And so that is going to be our vertex. So we can obviously have our calculator do that for us, but good practice right now, perhaps, to complete the square. So please take a moment, hit pause, and work on completing the square. So in completing the square, we factored out our A value, which was negative 2,500. So that left us with x squared minus 16x. And then to complete our square, we took negative 16, took half of that, which was negative 8, squared it, which gave us 64. If we add it, then we must also subtract it. And then we factor our perfect square trinomial to x minus 8 all squared. That negative 64 has to get kicked out of the brackets. In order to do so, we need to multiply negative 64 by negative 2,500, which gives us our 160,000 that we add to 10,080,000, equaling 10,240,000. So that tells us that our vertex is 10,240,000. So let's take a look at our graph and see what that means then. So this point here is XR, which is 8 and 10,240,000. And so understanding the meaning behind it is when X is 8, meaning there are 8 $25 increases, we maximize our revenue at 10,240,000. So when we answer this question then, when it says determine the price of a package of season tickets that would generate the maximum value, then we look at our new cost, and you can see back at the beginning where we had written new cost is equal to 1,400 plus 25 times 8, because 8 increments is going to do that. So 1,400 plus $200, that tells us that $1,600 is going to be the new cost for our season tickets. How many season ticket holders would there be if the plan was implemented? Well, then that is going to be our new quantity. Of course, we know that we're going to lose 100 ticket holders based on every increment. So we know it's 7,200 minus 100 times 8. So we're losing 800 season ticket holders, which brings us down to 6,400 season ticket holders that will remain. Okay, and how much more revenue are we generating? And you can see that happening in this line of our completing the square, and that is we're gaining 160,000. So the increase is 160,000. Okay, so let's just take a moment as well to look at how we could have found that on our calculator as well. So we're looking for that point right there, our vertex. So we can go to second trace or calculate menu, and we're looking at the fourth option, which is the maximum. And so we need to put the cursor so that it is to the left. So we can arrow over to the left right there. So we are left of the vertex, and it's prompting for left boundary. Yep. And the right boundary, we can move the cursor over to the right of the vertex, anywhere to the right of it, hit enter, take a guess that it's somewhere between those two boundaries, and there it is. So we can round, and that is to say that X equals 8 and Y is 10,240,000. Okay, so that is it for the revenue questions. Let's move on to area questions. So we can do that looking at page 356, right? Class example number 2 is an area problem. So in this particular case, we have a rancher that has 300 meters of fencing in which to form a rectangular corral. And we know that one side is going to be an existing wall. So a diagram is always going to be helpful in this particular case. So let's draw our picture. So there's my existing wall. And our enclosure is then going to look something like this. And we know that the total length is 300. They've specifically indicated to us that 2 sides of the rectangle are each X meters. So if that wasn't given to us as a variable, we would need to label that ourselves. And this last length, we could call this y for now. And what do we know is that 2x's plus a y is equal to 300. So isolating the y is equal to 300 minus 2x. So this is actually 300 minus 2x would be another expression, so that we just keep it to the same variable. So back to our area formula. So again, in its most basic sense, what do we know about area? Area of a rectangle is simply length times width. So in this case, we're looking at x times 300 minus 2x. And if we distribute that x in, we would have 300x minus 2x squared. And so that matches what they've indicated for us, which is that the area of this corral can be defined by this quadratic. So let's work on completing the square to determine the maximum area possible. So again, this is one of those things where understanding what your graph might look like is going to be helpful for finding our solution. So we know that instead of a y-axis, we have A, or area. Our width is x. And so even before I put this into my calculator, I know that my quadratic is probably going to take a shape something like this. And I know that in this one, this particular situation, it goes through the origin. Why? Simply because when width is 0, the area, of course, is also going to be 0. As the width increases, our area will increase until the width starts decreasing, or sorry, increasing so much that the rectangles starts kind of rotating around, changing positions, and then area back to 0. Again, we cannot have negative width, we cannot have negative area, so only quadrant 1 is relevant. So take a moment and let's work to complete that square. We'll rewrite it in descending order, so negative 2x squared plus 300x. So just hit pause and complete your square. So we complete our square by factoring out the negative 2. That leaves us with x squared minus 150x. And then we need our third term. So to get our third term right here, we are going to take our negative 150 divided by 2 and square it. So divided by 2 is negative 75. Square that plus 5,625. Because we're adding it, we must also subtract it. Then we're going to factor our perfect square trinomial to x minus 75 all squared. And then this negative 5,625 gets kicked out of the bracket, which means it needs to be multiplied by the negative 2 out front. When we look at our vertex form, we know that this point here is XA, which is also 75 and 11,250, which tells us that when the width is 75 meters, the area is maximized at 11,250. So max area is 11,250, and our dimensions are 75 meters by, which is our width, our x, and then our length is 300 minus 2x, so our length is then 150 meters. And we should add on the area is 11,250 meters squared. Please let me know if you have questions.